Hi everybody. Well, we'll start in a moment on the demonstration part of the example that we covered in the previous video, right? And the example is this here, is given and non-linear dynamical system, and I get it from Moore-Gracel model called from the lecture notes of Matthew Peet, right? The links will be in the description down below, right? And okay, and equilibrium point is 0, 0, right? And since we are not going to use SOS method directly or semi-definite programming method, right? In this video, we're going to use linear programming method that I explained in the previous, right? And first, let's look at the origin. Here we can see the equilibrium point. And first, we will establish a circle, right? Really looks like a perfect circle, by the way. And the radius is I just randomly picked 10. Okay, you might pick 5 or 15 or something, right? And just start from some place. And the point is this: after you're sure, after having done conducted all those simulations and seen the stability, seen the convergence in all the cases, you want to get a Lyapunov function and kind of the stability certificate, right? And for that reason, now we are in the stage of Lyapunov function construction stage. Okay, and again, we will need v of x. Okay, v of x will be in the form of m1 of x transpose p, right? And by the way, p, but in this video for some reason I call it alpha, right? Capital alpha, right? And capital alpha is just a, but okay, whose entries alpha 1 1, alpha 1 2, dot dot dot, right? And I just want to distinguish from the examples we did earlier, right? And not m2, m1 again. M1 for this example will be x1, x2, not the first order terms, but in addition to x1 and x2 will also include second order terms, right? x1 squared, x1, x2, and x2 squared. If we are sure that the stability, okay, is present, and but we time after time get time after time we get instability, right? Infeasible region. I'm sorry, I didn't meant instability. I meant infeasibility every time. In that case, we would also include third order terms. And again, if we didn't succeed, right, we get to fourth, fifth, right? That kind of iterative process. This is something that we deal with. All right, and I'm looking at this, and yeah, so we are going to construct this now our v of x, right? And a will be parameterized by alpha 1 1, alpha 1 2, dot dot dot, alpha terms, and a is symmetric, right? But unlike the previous examples, and this may come as a confusing to you, and I 100% would understand that. A will be symmetric, okay, no problem with that. But A is not necessarily positive. Okay, why is that? Because for, let's call it P, right? For P to be positive, it means X transpose P, X greater than or equal to 0, right? Or X in Rn, sorry, excluding 0, right? Excluding 0. But mean Rn, and our domain is not Rn. In this case, our domain is just the bore with radius R, right? So it may be the case where A has some negative eigenvalues, right? Even negative, actually negative eigenvalues, and all the terms can be positive. However, what is the domain? All of x in bore B bore, right? Excluding 0, right? And there is something similar to that example. It's called matrix copositivity, and let me matrix copositivity, right? And I will try to cover this in the upcoming videos, hopefully. And okay, I wanted to mention that interesting detail. So when we find our when we are completely done with our optimization, right, optimization stage, and we see successful solution, right, or feasible solution, when we see that kind of warning or the notification, we are like, hey, okay, we just found it. And as a reflex, almost, right, without even thinking about it, you would have the tendency to just write minimum of eigenvalues of this A alpha matrix. And in that case, if you see minus 1 point something something something, you shouldn't be like, hey, there's something wrong going on, there must be a mistake or something, right? Actually, there's not a mistake probably. And the best way to check you really obtain the solution, right, is just you have xi terms, right? You just generated thousands, maybe tens of thousands sampled points in state space, right? And in this ball, so I is from 1 to n points, and n point is probably more than 1000, right? And you are just going to keep them, by the way, right? And you are just going to plot v of xi, right? Let's say, for example, in this case we have two-dimensional x1 and x2, right? We have two-dimensional nonlinear dynamical system, and right, and for this I would like to mention, wait a sec, and x1 and x2, right? You're just going to plot vxi, and probably you are going to see something like this, like convex v of xi. And this is not going to be a continuous one, but points, just points. I'm going to show you what I mean here in this case, right? So don't worry about it. And after you have xi terms, right? And after finding a, just compute vxi time series you may think of, and it's an array, right? It's at the end of the day, v of x is a scalar number, right? Okay, and you have this array v of xi, right? Again, for I from 1 to np, right? And just check the minimum of this array, right? And you should see something that is less than 0. I'm sorry, I made a mistake again. That is greater than 0. That must be positive. Okay. And after that, since you have an a term, a you have A and X transpose AX. By the way, I wouldn't say X transpose, but M1 of X A M1 transpose M1 of X, right? This is your V of X. Okay, and again you are just going to get your v dot of X, right? And this is something that you know at this point, and we're just going to again look at this. You should see something that is less than 0. All right, so this is V of Xi's, right? And for two-dimensional system, sorry, x1 x2, you will see something like this. Okay, like almost the inverse of this in shape. Okay, and I'm looking at my notes, checking my notes. Okay, now I'm going to go to MATLAB and we are going to do that. I mean, I already coded and checked if everything's alright, and if everything's alright, and we are just going to go step by step, line by line. Okay, and let me get the other screen, display capture. Okay, control home. All right, oh, now we're on. Okay, so let me get this, clean everything, and this is for SDPT3 and YALMIP. Okay, you don't need to do it like this. If you have some SDP solver and YALMIP, you would probably like to add path, you know, using MATLAB GUI, right? Okay, but I prefer this way for some reason. Anyway, okay, the code starts from here. Okay, right, and SDP var. So this is the variable, like you remember sims x1 x2 for MATLAB symbol toolbox, right? And this is it. All right, and this is our state variables, and this is our state vector, and this is the dynamics of x1 and x2, and this is the, if you go a couple seconds back, and this is the thing that I written on the whiteboard, right? All right, this is f in matrix vector form, right? And this is just epsilon. It's for, you know, numerical accuracy. Just bear with me for a second. And yeah, this is YALMIP's way of okay, I'm going to just run it, and I'm now going to show you. We are just going to create monomials, and this term is for the maximum degree, and this is for minimum degree. If you just ignore the third term and didn't write anything, and only written 2, for example, you would see the terms starting from 0, meaning 1, right? 1, x1, x2, first order terms. And okay, why do I say this? Let me just show this, right? Okay, this is perfect. Maximum degree 2 and minimum degree is 1. All right, let me just also show you what will happen if I didn't. Okay, put 1 here, but you, every time you do this, you need sDisplay. sDisplay is also a YALMIP function, right? This, okay, you see it starts from 1, meaning x to the or 0 degree, 0 order terms, right? Here these are the first order terms, here these are the second order terms, and this is quite convenient for if you like to use that kind of stuff, right? I mean, not even for, okay, not even for this, even for the symbolic computations, it's really flexible. Okay, so we just compute this, right? Okay, and I'm looking at this. Yes, now as I said, alpha, right? We are just going to create alpha. Why it is 5 times 5? I mean, I could have written just, let me check this. Okay, instead of 5, I could have written this, right? And let me check this. 5. Why 5? Because it's here, there are 5 terms, as you would expect, right? Okay, let me just put it here as well to make it more, you know, general looking. And all right, I'm looking at this symmetric also to indicate that it's symmetric. All right, let's display. All right, this is, let me get, okay. All right, you can see 5 1 5 1 5 1 and 5 1. It is symmetrical matrix, right? And 2. All right, what is this? This is the thing that I usually call m1 of x transpose p m1 of x, right? Okay, so let's, coefficients also is YALMIP function, and you don't have to think about this at this point. For example, this term, for example, v1 only includes x terms, right? And alpha only includes alpha term, right? And this function, this is polynomial, you can consider it as a polynomial, just scalar, right? Polynomial includes x and p, sorry, alpha variables, right? And I'm saying that write this polynomial as coefficients and x terms. Okay, x terms and whatever the coefficient of that x terms is, right? Represent it like that. Okay, coefficients and, you know, terms. Let's see what happens. Okay, here these are the x terms. By the way, if you have like a, b, c and x terms, all right, and you like to see x terms written in this way, you will see not only alpha, a, b, c terms as well, right? X terms and the coefficient of that x terms, whatever the case may be, right? And this is quite general, this is quite flexible, as I said, it's very helpful, all right, in many cases. Okay, v of x, again, this is our v of x. This is how we parameterize our Lyapunov function. All right, and just to see, again, this is the same, just to make sure. All right, I'm going very annoyingly step by step, so bear with me. And by the way, before that, let me just go to this. Yeah, exactly. Just, I mean, you may, you know, copy and paste it, right? I just get it from MATLAB website. There was a, you know, problem on generating a random points inside of a sphere, right? N-dimensional sphere, and you can just use that function. Okay, I will try to put the MATLAB link down below, right? But you can just type the same, right? Okay, so what this does is this, I mean, we are just going to, as the name suggests, n dimension, state space dimension, it says, and r1 is the length of our sphere, right? N dimensional sphere, right? For example, in this problem, this is two dimensional nonlinear dimensional system, right? And as a sphere length, we picked 10, or I'm going to pick 10, right? This is just a number. Okay, there is not a some important reason for why I picked 10, just a number, all right? And endpoints will be 1000, for example. Let's check if that is the case, right? Okay, and after that it will give you, and we will check that if it will just give you points in state space. Okay, bunch of points. Okay, this, all right, 1000 neighborhood radius, I call it 10. Okay, 2 dimension radius 10 and 1000 points from state space. Okay, let me just show that. I'm just going to plot this random points, right? Okay, let me look at this. And since this is two-dimensional, this is x1 and x, maybe it will be better for me to, you know, x label. I can see that, I'm sorry. Okay, x label, right? X1, right? Then change that, x2, and this is y label, right? So let's draw it again, right? Okay, this is the state space. We are just looking from above, right? And this is a plane, since this is two-dimensional, and there we just picked 1000 points inside of a, let's check, yeah, inside of a, here you can see 10, radius is 10, right? And also here we can see minus 10 and 10, the radius is 10, right? Okay, let me just comment it out. Okay, all right, now we have 1000 samples. All right, we are going step by step. Okay, so in every optimization problem, and especially for this one, you are going to have constraints, and for YALMIP you are going to create your constraints in the way that I will show you right now. Okay, just do it like this. Just create some object, right? Empty object, and iterate from 1 to your number of, you know, sample points, and I set it like temporary constraint. Okay, and replace, okay, just, it is important for me to, you know, get this point across, and for that let me just clean the screen, right? Replace, let's look at it. Okay, so using SDisplay, right? Using SDisplay to display this, because if I write this, YALMIP consider this as an object and it doesn't allow me to, you know, put it on the screen. Okay, again, it is a gigantic thing, so to be able to maybe, yeah, I should do this, that will be easier. Okay, assign I equal to 1, right? And then just put that, and let's check what cons1 object is. Okay, it is this. And if you, for example, you can also do something like this. I'm going to write that alpha, right? Alpha, let's see. All right, since we substitute x with the random number, right? Okay, and let's say x1, xi, and I equals 1 is 0.1 and 0.2. We just substituted into our Lyapunov function, and what do we get? We get only alpha terms, because Lyapunov function was parameterized by x and alpha, and if we put numerical numbers for x terms, we only have some numerical coefficients times alpha terms, right? Okay, and again we can see, and you see another thing that is very important. This is linear, right? Some alpha term and some coefficient, right? Okay, this is the great news. This type of thing will allow us to use linear programming methods to construct or determine the alpha terms, right? Okay, and okay, I feel like you kind of think about it a couple of minutes, okay, over this, and you will find it. And after, you know, getting kind of used to that YALMIP syntax, it really comes natural. Okay, and I'm just going to press F9. Okay, and let's look at our first construction vector. I call it construction vector 1, number 1. Why number 1? You ask. I mean, because this is for v of x, right? This is for v of x. All right. Another thing is this coefficient. I mean, I use this, right? And this must be this term. And you're like, hey, it doesn't make sense. Okay, just keep this line in mind, and I'm going to go to the whiteboard again. Okay, just press this and control home. All right. Let me expand on this a little bit, right? One sec. Okay, come on, got it. All right, we have v of x, and v of x has actually x and alpha terms. All right, okay, and v just, or maybe I should write this right, and we have v of x alpha, and I just put xi for xi for x, right? And then I will have v alpha, right? Xi. Okay. And what is this? This is some number times alpha term. This is some number times alpha term. Dot dot dot, right? This is all like this. And we know that v of x must be positive, right? And to impose that type of constraint, right, I am going to, or it is the case that people do often, right, xi, right, greater than epsilon. Remember the epsilon term, like 0.001 or something, that kind of small number, right? It's probably 0.01 or something. This is like that, and times xi, right, and xi transpose xi. Okay, you may think of it like saying vx greater than some epsilon times x squared, or maybe you would think of it like that, right? This is the positivity constraint, right? Okay, and that's why I didn't call xi in that. I call, if you recall, and I'm going to show you again, rand vec, and rand vec is like some number, and we have two-dimensional, right? This is for I equals 1, I equals 2, dot dot dot, again number, right? I equals n, right? Dot dot dot. Okay, and if you pick that, and how would you pick that? You would say rand vec, right? What is the row number? Row number is ii, or 1 in this case, and which columns? Every column, right? Every column, and you will get this, right? And you want to get a scalar, right? For this and vec, and I'm looking at this ii, all of them, times, or like this, rand vec, right? ii, every column, and transpose. Okay, transpose symbol, and here then again times epsilon eps 1. Okay, and this type of constraint must be there, right? Here, to put a constraint like this, since this is a sufficient condition for that, right? And since I should use this operator rather than using strictly greater than sign operator, right? And we just pick this type of way of doing things, and okay, greater than equal to, what is it? It is v of xi. V of xi. And v of xi is, I didn't call v of xi, I'm looking at this, and I call it coefficients of cons 1 x. Okay, what was cons 1? Cons 1 is replace, right, vx, replace this value with front wake, right, I every column, right. Okay, this is a number. Replace x, this term will include x, and replace those x with that numerical value. This replace kind of similar to the MATLAB function subs in the symbolic toolbox, right? Okay, and what do you get? For cons 1? Cons 1, you get some number times alpha 1 plus some number times alpha 2 dot dot dot, right? This is something that you get, and if you say coefficient x, you will only get, I mean, since there is no x term, right, you will only get this. And if you write this, right, if you like do that and s display cv, right, you will see this term comma 1 because there is no x in this term, right? For example, x squared plus 3x plus 1. If you use coefficients and then display them, right, you will see, and I'm looking at this, 1 x and x squared, 1, right, or maybe I should use 2, right, 2, 3 and 1, right? You will see something like this, and this is the kind of rationale behind this, right? That's why it's written 1 here. Okay, so coefficients gave us this, and let me use another color, right, this, and allow us to impose this constraints is what I'm saying. Okay, so let me get back to MATLAB again. Control home. Okay, this, okay, I'm getting used to kinda. Okay, I'm just going to press Ctrl Enter to run the whole section, right? Okay, I pressed it. All right, and it took a couple of seconds actually. All right, yeah, I just, for example, I'm looking at this, I just write it. It's not necessary, right? Let's comment it out, right? And cons 1, okay, this will be the last. For example, I equals 1000 constraint, right? Alpha. Okay, let's run that. Okay, all right. Okay, we just run the section, right? And we just look at the, you can consider this cons 1 term as v of xi, right? We know what v of x is parameterized by x and p alpha, right? X and alpha, and we just substitute x terms with the random number that we sampled from the state space, and this is a polynomial that is parameterized by only alpha. Okay, and what I'm saying here is this, what what is this saying is this: we have some polynomial with alpha 1, alpha 2, dot dot dot, right? And just give me that polynomial such that alpha terms and their coefficients, right? And their coefficients will be such that they are numbers. They are not x terms or something, right? This numbers, okay. And this is the case. Okay, this is the end of the first stage, I will say, right, in constructing the optimization problem, because we just completed this. We just completed xi transpose xi, right? Okay, epsilon 1. We just constructed imposing these constraints. Okay, this is perfect. And now we'll be looking at the v dot part of the and second stage of this study, right? Okay, what is this? Let's recall again what is v of x is. And v of x is, here we can just use this line, right? Okay, v of x is this. It is a polynomial. It is a polynomial parameterized by alpha terms and x terms. That's all it is. It's not complicated than that. Okay. So let me just, by the way, clean the screen, right? And here I'm saying, this is basic MATLAB symbolic toolbox command, by the way, but it is a YALMIP command in this case. It's the same function, Jacobian, right? We are just trying to create, construct v dot term, right? V dot expression. How would we go about doing this? I mean, we would, take the gradient of v of x with respect to x terms, right? And what would we have? X and p terms probably, and then we would multiply it with f, right? Okay. And recall v dot equals grad v, right? Grad v transpose times f, right? F of x, actually that will be better. Okay, and let's generate this. We will probably see a very big polynomial, right? Okay, it is so big that we are not able to see even, right? That's why probably a lot of people use coefficients function, right? Okay, let's run that. Okay, now again we tell YALMIP, hey, show us this polynomial such that we want to see the terms x and their coefficients, right? And their coefficients may be alpha, beta, whatever, right? But in this case only alpha and some numerical values, right? Okay, let's check. Okay, x terms, right? These are x terms and coefficients here. And another point to kind of consider is this: alpha terms, or the coefficients of these x terms, are linear in alpha terms. And that is again a great news. That's again a great news, because what's going to happen is this: we have this v dot term, right? V dot term is basically this, and we will draw a random sample, right? Like we generate 1,000 samples, right? And we will one by one, let's call it I equals 1 in first random samples. We will substitute x terms with those numbers, right? Okay, and then we will have only some, we will have a big polynomial, right? V dot x, v dot term is parameterized by alpha and x, right? And when we substitute for x, we will have some numerical value times alpha, some numerical plus some numerical value times alpha 2, or etc., right? In that case. Okay, that's the rationale behind that. All right, what am I doing here? If you look at it, we are just constructing constraint vector 2, I call it, right? Why 2? Because first constraints were named constraint 1 and they were related to the v of x, right? And now we are focusing on the v dot, the second stage of the constraints, right? And here this section and this section, they are almost identical, right? Okay, again we are just going to replace v dot, we are just going to basically this comment or this line generates v dot of xi comma alpha. You can think of it that way, right? Okay, that's perfect. And let me just take a look at this 1 second. Okay, everything right. And let me just, okay, running. Okay, it took more than I expected actually. Okay, yeah, that's why, because I'm also recording, right? And also I connected that to my tablet. Maybe that kind of is hard work for my computer. Okay, all right. This is v dot of xi, right? And for example, let's run this, right? Okay, what is this? This is v dot of xi comma alpha, and we call it to give us such that the x terms and its coefficient, right? And there is no x term, there is only constant, right? It doesn't depend on x terms. If that term doesn't depend on x terms, it will give 1 and the term itself, right? The v dot xi itself, right? And here this is the case. And again, these are of some number times alpha 1 plus some number times alpha 1, linear, the critical part, right? Okay, and let's check the size of the constraint vector too, right? Okay, 1000, that's great, since we have 1000 samples, right? Okay, this is the final section. This is the final section. After we are done with this, we are going to check if everything went, without any problem. We are just going to control our v of x and v dot of x, right? And I'm looking at this. Okay, this is, we are just starting from scratch to generate our constraint vector, right? And here, this is just create empty constraint object, and after that include our constraint vector number 1. Okay, that's great. And after that include our constraint vector number 2. All right, here I just stated vec operator is like, if you operate that on a matrix, you will see just vectorize that, right? Okay, and this kind of means is this: I want alpha terms, alpha 1 1, alpha 1 2, etc., right? I want alpha terms to be between -20 and 20, right? Okay, and so I kind of constrain alpha values to be in that range, so it's kind of bounded, and the optimization kind of search for alpha values in that range, and it doesn't go generate, because it's there, as another professor that I watch his lecture on this topic, MIT, Russ Tedrake, his name is, and there is a lot of degrees of freedom. Optimization can do anything at this point, right? We are not actually constraining alpha terms that much. That's why we need to put that kind of constraints if you don't like to see alpha values, some alpha term being million or something, right? That's the rationale behind that. And okay, by the way, yeah, that was my mistake. Yeah, that's not correct. And let me just delete that. Let me delete that. I mean, you may put that kind of a constraint as well, but it wouldn't be good. Again, alpha matrix doesn't have to be positive definite. It is like the matrix co-positivity thing that we talked about earlier, right? And that's why you don't expect alpha to be positive definite if you are only focusing on a, region circled by a sphere, right? So alpha can have negative eigenvalues, right? But v of x being positive is the critical part, and we just check the v of x being positive by checking x transpose times alpha times x, right? If that is greater than 0, that's okay. That's what we need. And x takes the values in that domain, in that, inside the ball, right? Okay. And these are, to be honest with you, I just get them from YALMIP website. There were a couple of examples on this issue, right? To be honest with you, I'm just only familiar with this line, and other terms not that much, and also this term I just call it maximum iteration to be 100. The default value I guess was 50. Okay. I mean, to be honest with you, I could delete a couple of them and it wouldn't make that much of a difference, right? All right, so we are just going to run this. All right. Okay, and you know what? You have no idea what it means to me to see successful sort comment warning, right? This is really important. This is really important, and that means we just got the solution. All right, now what? Let's check. Let's get the, by the way, solution, right? Okay, this is alpha, right? And this is for if we have some number, some entry that is like really close to 0 but not 0, right? That is like 1e minus 9 or something, right? You would like to consider that as 0, right? Okay, but we don't have that type of term. And let's check the minimum eigenvalue. Again, it might be negative. Yeah, and it is actually. It might be negative, and it is not a problem, right? We are just looking at the compact region, right? Inside of a ball, right? Ball spherical region, right? Okay, we're done. At this point, at this line, we are done. We are just, by the way, I was just experimenting on something, right? Because I kind of wanted alpha to be sparse. I just wanted to promote sparsity, so that's why I just run bunch of codes, and I don't want to delete them at this moment. Maybe you like to experiment a little. I didn't get much farther with those lines, so maybe you would anyway. And now we are going to check if everything is correct. Okay, this is for vx0, this is v of x, this is our Lyapunov function, right? Let me just use, this is for, you have a polynomial and there are some coefficients, but some coefficients are like, due to numerical round of truncation, etc., really close to 0 but not 0, right? And that line makes them 0. Okay, and let's check our Lyapunov function. Okay, and you know what, this is the answer, by the way. Yeah, this is the answer. This is our Lyapunov function. Do you rewrite something here? It is very big. This is what you would rewrite probably. And there are some negative terms as well. You would probably, you used to seeing some all positive coefficients, right? And that's okay. And by the way, this is not SOS, and this is important. This is not SOS. I mean, in all Rn, right? But it is kind of SOS in the ball, right? In the domain that we described. Okay, so I just want to make that clear. And I'm looking at this. Yeah, this is, we are just generating v of xi array we mentioned earlier, because we want to check if this is really what we want, right? V of xi, and v of xi array, every term in that array must be strictly positive, right? Okay, so I'm just substituting our random values inside this v, our candidate Lyapunov, right? Okay, and I am just, this is for x1 xi or x1 component of the random vector in that sample, right? X2 component of that sample point from state space, and this is the number that corresponds to that random vector, right? Okay, here blue dot, right? Blue asterisk, right? And okay, let's see the plot, right? It's going to be a great plot, by the way. And by the way, I kind of forget something. I'm sorry. Let me. By the way, you can put that as well. This is v of xi, and these are the index numbers, and they are all greater than 0, right? That's the case. And okay, I'm just going to do that and do this line. Wait a minute. Do this line to generate a plane, zero plane, right? Okay, this is zero plane, right? And let me make it larger. Okay, this is v of x, right? This is v of x. All right. You see it looks like a ball, right? Like positive, right? But you might see, hey, there are some blue dots coming out of this, emerging out of this plane, and this is not actually correct. I mean, all of them are greater than 0, so it's kind of due to the asterisk being some, asterisk is like a ball here. It is graphical reasons for that. Okay, what I'm trying to say is this: it may look like, hey, there are some positive negative numbers or something. No, it's not. Okay, this is v of x. Actually, v of xi, I will say, right? Okay, not continuous. This is only for some determined points. Maybe at this stage we would, yeah, we would draw for a lot of x terms, right? Maybe. Okay, I'm very amazed by the beauty of this plot. So let's check the minimum value of that v of x, right? And this is positive and important. This being positive is important because if it were negative, that means we made mistakes in some place, right? And okay, and this is, remember, we wanted to impose strictly positiveness constraint on v of x, right? And that's why we just use this v of x minus epsilon times xi transpose times xi, right? And this whole thing means xi transpose times xi. Okay, all right. And we want to see this as a positive number, minimum number, right? This must be greater than 0, right? Every one of them, a minimum number must be greater than 0 as well, right? Okay, and let's clean the screen and let's check what we need to check, and that is v dot, right? Okay, we have vx, and we want to generate vxi, right? Okay, this is control stage, by the way. If you're 100% sure that you coded correctly, right, you don't even need to do that after the 100th line, right? And but I really want to show you the how your Lyapunov function would look like in that case. And you might even think that, hey, this is two-dimensional, what would we be doing in three-dimensional, etc. I mean, there are other plotting strategies you would apply, right? And of course there would be, if you're really into seeing the Lyapunov function, you would employ them. Maybe hopefully in the future, in the later videos, we will be dealing with some of those, third dimensional, fourth dimensional, etc. non-linear dynamical systems, right? And I'm really hoping that I will be able to do that. Okay, let's run this. Okay, you know what it is. And let's check the degree, right? Okay, and this is v dot. This is just v dot, right? And you may be thinking, hey, this must be negative definite. Actually no. In the ball, you should say this must be negative. After you should add, you shouldn't forget to add inside the ball, not inside Rn, in whole space, right? Inside a predetermined region, right? Okay, and we are just doing the same thing, right? We just looking at our random points. Maybe, to be honest with you, now that I think about this, we would be, yeah, we would generate like 10,000, right, more random points, right? And we would also check if those numbers v dot is negative and vx is positive, right? This is, yeah, thinking about it now, that will make sense better, right? Okay, let's plot it, right? Not, I didn't plot, I generated v dot of xi terms, right? And this is a array, right? And I'm really hoping that you are able to see that, by the way, the codes. Anyway, it's a little wait for that now. Okay, and let's plot that. Okay, and let's plot the zero plane. Where is this? Yeah, zero plane is where. Okay, this is like a graphic, some type of graphic of, I don't want to say earth, but the blue dots actually not above the green plane. Okay, and we, yeah, you see this. Okay, x1 xi, this is the ball, right? This is the ball with radius 10, right? Okay, we are just looking at this ball, right? Okay, that's great. That's, again, you might even cannot do that. I guess we are not able to do that. I was trying to make it, you know, upside down, but I guess not possible. Okay, and it is like the inverse of vx we get earlier, right? Okay, let's close that, and let's check if v dot, every term of v dot of xi is negative, right? That's why I look at the maximum of it, and it is negative. Okay, it is less than 0, and that's really important. And not only it is 0, it also greater than this function, again, v dot of xi, right, must be less than minus epsilon times xi transpose xi, and this kind of means that, so this value is also negative, right? Okay, that's great. So yeah, that's it folks. So let me just again, where is it? Let me just again at the end of it. Yeah, this is our Lyapunov function, is the end of the story, right? Define on where? Define on, not on Rn, but define on inside the ball, right? Okay. And if you like to, you know what, I'm going to go off the script, and I am just going to do that for ball with radius 20. Okay, it will be a really, you know, things may go sound, and let me just start over. All right, okay, computer is being annoying right now because, yeah, OBS kind of makes it harder for him. Okay, we just did that, right? Okay, yeah, this is the, oh, I can't believe it when seeing that. Successful sort, it says. Alright, let's again run this section and see if really it is really positive, right? Wow, this is great. That is great. By the way, we could have done, wait a sec. Okay, let me just type here and type here, right? Ctrl S, and run it again, right? And let me just make it bigger, right? Here this is v of x, right? x1 and x2, I'm sorry, and these blue dots are xi's, right? I being 1, iterating from 1 to n points, and this looks like a ball, right? This is looks like a convex function. Okay, and let's check this because this is only for graphical reasons, and yeah, it is positive, and not only it is positive, it is, this value is also positive, and that's great. This is great news, right? And let's check if v dot is really negative, right? And for that I'm also going to make the plane bigger, right? Alright, let's see what v dot is, right? Let me just make it bigger. Here this is v dot, and yes, let me check if that is really negative, right? Negative, not only it is negative, but also this term is also negative. And yeah, that's end of the story. I mean, if you have some background on optimization, right, I would expect your comments on how we would get the alpha matrix so that it is sparse. For example, I try to use those kind of lines. For example, I didn't state the problem as being a feasibility problem, but I try to minimize the one norm of that vectorized form of the alpha matrix, right? I try to minimize this term, and while minimizing that term, I also wanted to maximize the trace. I mean, I'm not, you know, I don't have a background in optimization, so you may think, yeah, this is not, it doesn't make sense or something, and I totally understand, and I would expect your feedback. And I did it, I put it over there to promote, in my mind, this to promote sparsity, and this to promote diagonal dominance, right? And yeah, that's the case. Hopefully you get some benefit out of this lecture, right? And in the next lectures, in the next videos, I will try to go into the depth of that SOS strategy, right? Because the first example was kind of really oversimplistic, and I will try to go more depth into, and also again study some other examples. Okay, and that's all today, folks, and thanks for watching.